Good morning everyone. I will be discussing today the geometry and meshing in CFD, which we generally use to pre-process CFD simulation. So these are the contents that I will be discussing. First I will be discussing meshing, why it is done, what is the use of it. After that I will be using the OpenFOAM meshing and geometry creation file, which is known as the blockMesh dict file, and later I will be discussing about Gmesh and how it is used for meshing and how it is used in OpenFOAM. So these three are the topics that I will be presenting. So first of all, in CFD we see that the physics of the problem are generally represented by mathematical equations. Here the equations become the governing equations, which are generally in the form of differential equations, and we know that the computer is not able to solve those differential equations, so we tend to discretize it in algebraic form, and these algebraic equations are finally solved by the computer. And so this algebraic equations are basically solving the geometry or the these algebraic equations are basically being solved by the solver in context of the geometry. It's being discretized and it has been split into smaller spaces, and this discretization can be well defined or structured cells, and these basically solve the simulation. I'm sorry. So the use of mesh, we see the mesh is basically defined in two types. One is the structured mesh and the other is the unstructured mesh. The structured mesh is used for efficient and easy solving of the field variables, whereas unstructured mesh is slightly inefficient, but it is able to handle complex geometry. So there is a we tend to use both of meshes, structured as well as unstructured mesh, to solve the to understand to solve the equations in space and time. So next we see that the collocated grid and staggered grid, these are two different types of measures in which we define meshing. Here the mesh, like each small grid, is basically holding the data of field variables at its nodes. So the variables which I have been solving are the velocity components as well and the pressure components. So all these field variables are placed at the nodes of the grids, and we see that in collocated grid all the information, all the field variables are stored in the center of the node of the cell. And in case of staggered grid, pressure field is set at the node and the velocity fields are set at the faces of that particular cell. So this is this is where we get to know the actual values of each particular field variable. So now I will be discussing about blockMesh, like how this file works in OpenFOAM, and
try not to use the mouse exceedingly.
Okay, sir.
Don't touch the mouse unless you really want to use it.
Okay, sir. So this the block mesh file I will be discussing. So let's go to the file where the block mesh is present, and we'll see that how it actually works. We see that the block mesh dict file consists of 4-5 components. First is the vertices. Let me show you it in the slide. So it has 4 components: vertices, blocks, edges, and patches. So this is the basic structure of the block mesh file. So first, with the help of vertices, we define the each and every point of the geometry. After that, we create the block out of it. Then we define the edges, how those points are connected. By default, it is set as straight line, and with the patches is basically what represents the surface. So we will see how the block mesh dig file and all these components are actually placed in the block mesh dict file. So here we see that sir, is it okay if I present this way?
Whatever suits you, it's okay, as long as we can understand.
Okay, sir. So here we see that in the vertices there are 8 points listed in the vertices component, and we see that the first point is 0, 0, minus 0.5, 0.75, minus 0.075. So this becomes the first point is actually numbered as point number 0, and the rest are 1, 2, 3 and 4 and so on. So the first point is 0, 0, the next point is in the x direction. The second point is 0.5 and minus. And the third point is here. So I'm writing 0. This is point number 1. This is point number 2, and this is point number 3. And similarly, we can see that the rest 4 points are just protruded in the z direction. So it's all like in here. And these points are, this point is point number 4, this is 5, this is 6, and this is 7. So next we make a block out of it, and this is a particular sequence. We know that 0, 1, 2, 3, 4, 5, 6, 7. So first we make the points of the Z face, which is in the back, and then in the front. So first the point number 0 is this. This is point number 4, 5, 5, 6, 6, 7, and 7 0. So this will create a hexahedral block, and the 0 and the 30 230 represents the number of partitions that will be doing in that particular axis. So the 31st here represents the number of partitions, or number of partitions will be 30 in the x direction, in the y direction it will be 200, and in the z direction it will be again 30. And the grading here refers to like the geometric progression. I'll show you later what the grading actually means. Next we define the patches which represent the surface. So here we see that we define it a name, inlet, so and it is actually representing a face. So 1540 is actually representing a face. So we see that point number 1 is here, 5, 4 is this one, and 0 is this back one. So 1540. Oh, I'm sorry. This. Okay, let me just make a correction. This is our point number 0, this is a point number 1, and this is this is 4, and this is 5. So 1540, we can see that it is moving in this direction. So all the faces that we will be representing will be in the normally outward direction. So if we use the right hand rule and the thumb will be pointing in the outward direction of the surface, is how we define all the surfaces. So if we see that 3762 and 0473 and all these are faces made of those vertices, and the second patch is outlet. So 3762. So it is in the top face, and if we use the right hand thumb rule, we see that it is pointing outward, in the outward the normal direction is in the outward direction. And the next 4 faces are defined as walls. So it is given the type wall, which is the first wall, and the walls with the S is actually the name of the patch. We can also define it in another way, like we can specify just the name first, like if we type inlet only here, and we can define the type, like say patch or wall, inside the block. So next is executing this file.
Why is nothing present in the edges block?
Sir, edges by default it is straight.
Okay.
Yes, sir. So this is actually the folder structure of OpenFOAM, which contains of 0 folder, constant, and a system directory. 0 contains the initial conditions, and system contains the control and the pre-processing settings, and the constant folder contains the constant that are used in the simulation, as well as the information of the geometry. So we open the terminal over here in this folder, and we type blockMesh. So we see that the simulation is the blockMesh file has been executed, and we can view the file in para view using the command parafoam. So here we see that it has created a block, and if we zoom it, you see that there are 30 partitions in the x direction, and we see that the x direction is along the left side, horizontally left side, and the z direction is also vertically upwards according to the geometry, and it has bisected or cut the geometry into 30 partitions, and we see that in the y direction it has done it has done a partition of 200 elements. So we get an overall of 30 into 200 into 30 cells, and we have defined individual patches. So patches are available here in the mesh regions. So this was representing the internal mesh. The first patch was inlet, so we can see where the inlet was. It was here, and here we see that as the points that we discussed, like we wrote in the blockMesh dict file. So we can see that it has moving in x direction by 0.15, and z direction also. The z axis is 0 is here, and plus minus 0.075 in the positive and negative direction in the z axis. The next patch was outlet, so it is also available, you can see, and the next one is walls. So these are all the 4 walls that we wrote in the blockMesh dict file. So and this was a simple block creation of the blockMesh dict. I've got another example in which we create a cylinder out of a cylindrical geometry, and we mesh it. So here we are making a geometry which is cylindrical in nature. So in the similar fashion we are specifying some vertices. So this was the simple block that I already showed you, and this is the cylindrical geometry that I'll be creating using blockMesh. So here we see that the first point is 76.200. So it's in the x axis. So I'll just be numbering the points. So this becomes point number 0. The next point is 0, 0, and 76.2 in the backward direction. So it is in the z. It's in the front of the z axis. Becomes here. This becomes point number 1. The next point is 76.200 minus 76.2. So the point is here. The point number Sorry, the point number 2 is this is point number 2, and the third point is let me just explain it again.
You can draw the 4 points and then number them.
Okay, sir.
You know how where the points are, right?
Yes, sir.
Just put them there and then figure out what is the coordinates.
Okay, sir.
I think in the previous slide you also had the geometry.
Yes, sir. Sir, that was geometry using the Gmesh.
Okay.
Okay. So first we define the origin, it's over here, and then we move and this is the xz plane. So the first point is over here, 76.200. The second point is over here. The third point is over here. The fourth point is over here. 0, 1, 2, 3. And we see that the next 4 points, like point number 4, 5, 6 and 7, they are their y coordinates has just been changed from 0 to 419, so the entire points is shifted in the y direction. So these points become here. Four, this becomes 5, this becomes 6, this becomes 7. Then there are another 2 points, the origin and the a point above the origin. So this is the origin, and here is the point, which is 0, 419 and 0.
So what are the numberings of these points?
The origin becomes 7 and 8, and in the last one that's above origin it becomes 9. Now in the next step we define the blocks over here. So all these blocks are like hex blocks, and we see that the numbering starts with 8108. So the point number 8 is origin, then 1, then 0 and then 8. So since we have only 3 points, so we define the we define a block using 4 points only in one plane, and the another plane using the next 4 vertices. So 8108 and 9549, this becomes one block. And the grading in this in x direction is 35, and y and z direction it is 30. Sorry, it's not grading, it's the number of partitions. And similarly we make the next block, that is 8218. See, 8218, so it becomes this, and then 959659. So, and similarly we make all the 4 blocks using the next 2 block statements using the coordinates. In here we see that the next block is the edges block, and it is defined, the first line says that arc 0 1 and there are some points. So for I wanted to create a cylinder out of it. So we need to define one point between point number 1 and 0, which will lie on the arc of the circle with a radius 1 and 8, between point 1 and point 8. So this will be some point over here, and we need to give the coordinates of those points. So I have used the 45-degree point which would have been lying on that circle. So like 76.2 sine 45 gives 53.8815. So I have fed in this point over here between point 1 and 2, so that it creates a circular arc. The same I have used in the arc of 1 and 2, points 1 and 2. Since it is a symmetric about the origin, so the points are similar, just they are the signs of plus and minus are changing.
Is there a certain ordering here? Like you have arc 0 1.
Yes, sir.
Can I also make it 1 0?
Yes, sir. So it is basically creating arc out of two points with 1 point feeding. So the next block is the boundary block. Here we define the boundaries. Here we see that first we are defining the name walls, and then we are defining the type of that patch as wall. In the inlet and outlet we are using type as patch. So here we have like 4 blocks, so we need to specify all the walls individually. The first wall becomes 0 1 5 4. So this is the point 0, then 1, then 5 and 4. But it is not a rectangular block anymore, because we have described its edge as an arc. So it will use this curved surface as a wall. Similarly, it will be for 1 2 6 5, 1 2 6 5.
So basically we have 4 of these.
Yes, sir, 4 of these, and the top are the inlet and outlet patches are 0 1 8 8. So since we have defined blocks individually, so we have to feed these parts also individually. So we have 4 quadrants which make an inlet and outlet. So we need to give these outlet patches the numbers, and it will.
So why can't we give it just like 0 1 2 3?
So like which
For the
one?
inlet patch.
Inlet
Patch you have specified as 4 different sectors.
Yes, sir.
So can we not say just 0 1 2 3, and that will create one
Okay,
disk?
sir.
Just
Sir,
ask.
yes, sir. We can check.
That's okay. You can continue and then towards the end.
Yes, yes, sir. Yes, sir. So now we use this file as for making our geometry and mesh. we need to name this file as a blockMesh only. Now when we execute the command blockMesh, I see that the execution is done. To visualize it, we use paraview. So here we see that it has created a cylinder. And we see that the blocks are hexahedral in nature. If you want to view the patches individually, we can see that the inlet, this is the inlet. Similarly, the outlet. And to see the walls, we click on the walls patch.
One question, why did it create a mesh which is aligned with the circular coordinates? Why did it not create those rectangular blocks here?
So those blocks would have been created if we have defined if we had not defined sector wise. We used 4 different blocks, so for all 4 different blocks had that different like grade.
What I'm saying is everything is very similar to what you had done in the previous case, right?
Yes, sir.
In terms of creating those hex blocks.
Yes, sir.
So what if I really wanted cells which were not aligned with the geometry, which were of the same, because you had specified X, Y and Z. If you can go back to your blockMesh tick file.
Yes, sir.
If I look at the commands in the block section, lines 40 to 43,
Yes, sir.
then you have these 35, 30, 30.
Yes, sir.
These are your grid sizes in the X, Y and Z direction.
Yes, sir.
Is it still following this numbering? 35, 32?
Sir, it is if I change the order now, then there it is not actually, it is like joined with only 3 points. So
What do you mean?
like here I have specified the values as the point number as 8, 1, 0 and 8. So it is not actually a block anymore. So it is a kind of wedge kind of shape.
But it is still hexahedral.
Yes, sir. Sir,
That's fine, that's fine. I was wondering.
Yes, sir.
More of a question, more of
Yes, sir.
explanation. And what if we try that? Do you have other things to demonstrate as well?
No, sir. These were the 2 main blockMesh files that I know.
Can you explain what is on the top in the blockMesh tick file?
Sir, these.
No, not the comments. The foam file, version, format, class, object. What is this? And the scale also.
Scale is basically it multiplies with the values over here, so that the general values in here are in meter, and if you want to convert it into, let's say, millimeter, then we multiply by 0.001. And these are files that are used by the solver.
So we don't need to change anything.
No, sir.
You guys have any questions?
जो ये simple grading then bracket 1 by 1 space 1 space 1. तो अगर इसको change करते हैं then what will I do?
This I'll show you in the previous file first. I forgot to do that. In this file, let's say I change the grading from this one to 2 or like 5. So I've made the x component of that grading as 5. So here we see that the grids have been shifted towards left.
So 5 denotes what?
Sir, it is actually
Some ratio.
the ratio of the last to first, I guess.
Okay.
Yes,
But the number of cells are still the same.
yes,
as what
yes,
it
sir.
was.
Yes, sir.
That's good for having resolving boundary conditions.
Yes, sir. And like if you want to do that on the right side as well, then we need to specify another block. Like we have to specify 2 blocks, one like 2 blocks, one in the middle. From the middle, we will make 2 blocks and then give the grading accordingly. So that. But these features are also available in the snappy hex mesh, which I'll be discussing in a few after a while in the next lecture maybe, and that is much more like it is much more compatible with HTL files and handling complex geometries.
Are there other ways of creating cylindrical geometries as well in OpenFOAM? This was.
Sir, there are other ways there is a direct command which can create a cylinder. Like we specify the radius and the height, and
So this what you demonstrated was quite complicated
Yes.
to create a very simple geometry like
yes,
a cylinder.
yes, sir.
Can you demonstrate that in one of the future?
Okay,
sessions?
sir.
Because these are very common geometries, having
Yes,
a cylinder, a
yes,
circle.
yes, sir.
Let's discuss some other ways. But
Okay.
this seemed to be very useful.
Okay, sir.
I think at 12 there is some other
Hmm.
something else planned here in the school. We have 10 more minutes. Do you want to move to the next topic or do you want to close it here?
Sir,
What else do you have?
sir, I wanted to discuss Gmesh as well, like how the meshing is done and the creation of geometry is done.
So that's a new topic.
Yes, sir, that's a new
We'll do
topic.
it next time.
Okay, sir.
In the meantime, if you have anything else that you want to demonstrate, discuss related to blockMesh or meshing in general, you can do that for 5 more minutes. Or if there are any questions, Karinda, you have any questions? You may have tried some other things in the blockMesh file. You can just change and show us.
Okay, sir.
We'll enjoy that.
blockMesh file. The order of the vertices is very important. Otherwise, if we miss an order, it can create a very different type of unique geometry, which might, like if we just.
I had one question.
Yes.
What you carry on, but in the
if we try the what do you call it? Numbering of the numbering in the patch inlet for the cylindrical geometry, if we interchange it.
Then it might throw an error, and the error would be like the normal is facing inwards or something like that. Here I have changed the order of the geometry, the vertices, and let's see what happens. So see, it gave an error, like has inward pointing faces. So it could not. I changed this from 1 2 3 4 to 4 3. That was.
So even for the inlet, it has to be like it has to follow the right hand thumb.
Yes. But
But
here, this was block, this
block.
block only,
So not
block.
even the
This
face.
was not also the face. In the face also, if I changed,
So for the block, the standard is you have the 4 points from lower surface,
no,
then 4 points from the upper surface.
4 points from the Z, behind Z, and the negative one, and then the
Okay.
forward Z. Uh, because if we change that, it will still work, but this grading thing won't, like, the, not the grading, this 30, 230 uh, will this 30 will not be representing X anymore. It may represent Y or Z, and so the others. Like if we make a in the XZ phase, like in the horizontal phase, the bottom one and the upper one, if we specify the blocks, then we number the blocks in that way, then the this 30 230 might be in the order of Y, X and Z. It could change. So the convention is like first giving the back face in the Z direction, and then the Z face, and then the front Z face. And here if we change the orientation of, let's say, inlet patch, it will also throw an error. Oh,
I think
sorry.
it's still throwing the
Yeah,
previous error.
previous error, yes sir.
We have to correct that. So.
Oh, it worked. So in this time I didn't change that. 1540. It shouldn't work.
That's okay, that's okay. I mean, I'm sure you can figure it out.
Yes sir. And that would be all for today's lecture.
Thank you very much. It was a very useful session.
Thank you sir.